chapter number 5 now, which is uh, continuity and differentiability. This is a very important chapter we have in 12th standard. There are two parts in this chapter. The first part is about continuity of a function. That is, we are going to check whether the given function is continuous or not. And the second part is about differentiation and its application. So, before we get into this continuity part, we just need to recall concept of the limit here. So let's recall concept of the limit first. Concept of limit of a function. You already studied in 11th standard. So we had this symbol, if you remember, limit x tends to a fx equals to L. Now what is the meaning of this? If you remember, you take values of variable x which are very close to a. Suppose this is a here, then you take values either from this side or this side of x. You put it into the function, then function would be very close to L, and that L is called the limit of the function. This much you know. Here you can take the values from this side as well as this side. The values of the variable x are very close to a, then fx is also very close to L, and that L is called the limit of the function. Okay. Now here based on the values of variable x, we had two limits. Limit from left, limit x tends to a from left of fx. Now when you say that limit x tends to a from left here, that means all values of variable x are of course close to a, but values are taken from which side? Left side of a. So here x is always less than a. Right? This sign does not mean that a is negative, remember. This is just a symbol which indicates that values of variable x are close to a, but from the left side only, this side only. So that's why in this case, if function is close to, for example, L1, then this L1 is called here LHS limit, left hand side limit. Okay. If you go to this side here, limit x tends to a from right. That is, here values of variable x are very close to a, but only from the right side. That is, x is greater than a. Here values are from the left side, so less than a. Here values are on the right hand side of a. This doesn't mean that this is positive. This symbol just indicate that the values are taken from the right side, this side. Then suppose function is close to L2, then this L2 is called RHS limit. LHS and RHS limits, we had these two limits. Now in general, these two limits need not be equal, remember. L1 and L2 may not be equal always, but if these two limits are equal, suppose this is 2 and this is also 2, then that 2 is called the limit of the function. So here we have condition, the condition for existence of a limit of a function. Condition for existence of limit of a function. Limit of a function. So the condition is, limit x tends to a from left hand side of the function, limit x tends to a from right hand side of the function. If these two are equal, suppose this is 2, this is 2, then that number is called the limit of the function. So limit x tends to a of fx. So this is very important criteria. Limit x tends to a of fx equals to LHS limit equals to RHS limit. In case if these two are different, then we say that the limit of the function doesn't exist. In case if we have this, limit x tends to a from right of fx is not equals to limit x tends to a from left of fx. If these two are different, we say that limit x tends to a of fx does not exist. You know that we say that this does not exist. Right? If you want to show that the limit doesn't exist, you just see that the RHS and LHS limits are different. So this is the one thing about basic definition of a limit. Now we list some standard results which you know. So here I'll write results about limits. We'll use this. So the first result, you know, limit x tends to a of any constant is that constant. Limit of a constant function is constant. Second result, limit x tends to a power function. If you remember, x raised to n is a raised to n. This also you know. Third result, that is limit x tends to a if you remember, x raised to n minus a raised to n upon x minus a. These two numbers should be equal. If you have x minus a factor, here also x minus a factor. Then the limit of this expression, you know it, n into a raised to n minus 1. This is the third standard result about limits, remember. These two powers should be equal. This number should be here only. You must have minus sign. Then take this number in the product and one less power. Fourth result, here limit x tends to a. If you have polynomial function, you know it, upon polynomial function like quadratic expression, cubic expression, then what's the procedure? If you remember, you must have x minus a factor here common and some expression, x minus a factor and expression. You cancel these and then apply the limit. This is not actually formula, but this is the method to find the limit of a function. Okay. Now next one is about trigo functions. Limit x tends to 0. If you remember, sin x upon x is 1. This is always 1. Even if you do the reverse, limit x tends to 0, x upon sin x is also 1. X upon sin x is also 1. Next one is about tan function. Limit x tends to 0. If you have tan x upon x, this is always equals to 1. If you do reverse, limit x tends to 0. If you have x upon tan x, which is always equals to 1. What we notice about all these four formulas here, the angle should tends to 0 and these and this should be equal. Angle always tends to 0, these and this should be equal. Angle tends to 0, these two are equal, and similarly here. Same formula you can write for inverse also. If I write limit x tends to 0, now you have studied inverse trigo function. Sin inverse x upon x, which is 1. Even limit x tends to 0, tan inverse x upon x, which is always 1 here. Fine. Now, if you remember in supplementary reading, we did this. If you remember, limit x tends to 0, a raised to x minus 1 upon x, it is always log, you know, it is nothing but the log a to the base e. This is always true. Limit x tends to 0, this is exponential function. A raised to x minus 1 upon x is this. From this, we had this formula, limit x tends to 0, e raised to x minus 1 upon x, it is just 1. Because here it is log e to the base e, you know that it is 1, we did in 11. So these are some formulas from the limits, you know these formulas. Okay. Now next is about continuous function. That's the beginning of this chapter, continuous function. Now here the word itself says continuous. Continuous means without break. Look at these graphs. I'm showing some graphs here. See, you know that there is a graph of which function? Straight line function, linear function. So there is no break in the graph of this function. So this is an example of continuous function. Continuous function. Look at to this graph. If I consider this one here, you know that this is a standard parabola. Fx equals to x squared. Fx equals to x squared. So this is also an example of which function? Continuous function. Continuous means there is no break in the graph of the function. You can draw the graph without lifting pencil from the paper. Continuous function. This is a continuous function. You can draw the graph without lifting pencil from the paper. Look at to this. If I look at to this graph here, you know that there is a graph of standard function, one standard function. If you remember, there is a graph of fx equals to modulus x. Now this is also continuous function. You can see that you can draw the graph of this function without lifting pencil from the paper. So this is a continuous. Now I'm drawing one graph here. You see, if you remember, we did it in 11th, and this is very standard function. If I see this here 0 to 1, this graph, then here if I show 1, then it starts from 1, so 1 is not included here, up to 2 is not included. At 2 it would start from here. Can you recall this is which function? This is fx equals to, if you remember, fx equals to box function. So graph is a step function. You know, there are several steps. There is a break at 1, there is a break at 2. Similarly, you can draw the 3, 4 and so on. So there is a break or jump at every integer. Break at each integer. Break at each integer. You cannot draw the graph of this function without lifting pencil from the paper. You see, I need to lift the pencil here. I need to lift the pencil here also. So this is not a continuous function. Not a continuous function. Not a continuous function. So now you must have realized what I'm trying to tell you, or what's the meaning of continuous function. In a single word, continuous function means you can draw the graph of a function without lifting pencil from the paper. Continuous, 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 not a continuous function. Look at the graph of sine function. You know it. Trigonometric function sine here. So this is 0, for example, here pi by 2, if you remember. Then pi maximum 1, you know, minimum it is minus 1. So at 0, 0. At pi by 2 it becomes 1, you know. At pi it becomes 0. If you go to 3 pi by 2 it is minus 1. And at 2 pi again it becomes 0, and so on. You have such a periodic function. Now again there is no break in this function. So this is also continuous function. Continuous function. Continuous function means there should not be any break in the graph of a function. Such a function is called continuous function. So that's one thing. Now every time it's difficult to draw the graph of a function and to check whether it is a continuous or not. So here we have definition which is in terms of limit. So let's see what it says. So I'm writing definition here. So definition of a continuous function. Definition of a continuous function. Definition of continuous function. Definition of a continuous function. So a function say fx is called continuous at c is the fixed point. At a one point we are checking a function fx is called continuous at c is a fixed point. If this is true, what if limit x tends to this point c? If you are checking continuity at 1, then you take 1 here. If you are checking continuity at 100, you write 100 here. If you are checking continuity at 0, you write 0 here. Fx equals to f of c. So what this definition says, check the continuity of a function at c. We need to find this limit. Limit x tends to c, fx equals to f of c. F of c means value of the function. If these two are equal, then we say that the function is continuous. Now sometimes instead of a single limit, you can use RHS and LHS limit. So you can write alternatively same definition. What I'll do, I'll just replace this limit by LHS and RHS limit. You know this. So I'm going to replace this single limit by these two, LHS and RHS limit. So here limit x tends to c from right of fx equals to limit x tends to c from left of fx. Instead of this, I wrote LHS and RHS and equals to f of c. So we have alternative way of defining the continuity. Whenever you have any question of continuity, either you use this or you can use this. This RHS, LHS limit we use mainly, you will see when we have such inequality in the question, greater than, less than, greater than or equal to, less than or equal to, or if you have box function, if you remember, if you have the ceiling function, or if you have modulus. Normally then we prefer these LHS and RHS limit, otherwise we'll get directly into this. Which type of the function? Inequality. This is called inequality. Box function, ceiling function and modulus function. Then we use this right hand side limit, left hand side limit equals to f of c. Otherwise we'll use this definition. This much only we are going to check. This is a continuity at one point only, remember. You are checking at one fixed point, c here. And if the function is continuous, if a function is continuous at each point of a domain, then it is called continuous function. Then it is called continuous function. Then it is called continuous function. It should be continuous throughout the domain. Remember, a function f is continuous at every point of a domain, then it is called continuous function. Using this definition, you can check the continuity at only one point, remember. And whenever there is a question of continuity, ultimately it becomes a question of limit. If you are asked to check the continuity at 0, find limit x tends to 0, f of x equals to f of c. If these two are equal, we say that the function is continuous. For example, if I take a simple example here, let's take this. Fx equals to x square. You know that this is a standard parabola. This one, you know this is the standard parabola, fx equals to x square. You also know that this is a continuous everywhere. There is no break in the graph of function, so this is a continuous everywhere. Question is here, check the continuity. There is a question at, let's say, 2. You know it would be continuous only. 2 means you are checking here. 2 is here. At 2, what happens to the graph of a function? It's continuous. There is no break. If I take 1, at 1, what happens to the graph of the function? It's continuous. If I take 0, graph is continuous. In fact, it's a continuous everywhere. I'm just showing you at 2. Answer, you know it is a continuous because it's a continuous function everywhere. Because there is no break in the graph of the function. I'm just illustrating. Okay. Now at 2 you want to check the continuity. So I'll find this limit first. So limit x tends to 2 of fx, that is equals to limit x tends to 2. What is fx here? X square. Now you know this very well that here if I put 2 the answer is 4. Okay, fine. And now I'll put 2 in the function. F of c means put c equals to 2 here. So f of 2. What is f of 2? That is 2 square. Again answer is 4. So what you have noticed from this 2? What we have noticed from these two are equal. Therefore you can say that f is continuous at 2. Continuous at 2. This way we can check, remember, whether the function is continuous or not. This is a standard way of verifying whether the function is continuous or not. Remember, find limit, find the value of the function, both should be equal here. Remember, I'll take one more example. Let's take fx equals to example number 2 modulus x, and you know the graph of the modulus function is this one. In fact, you know that there is no break in the graph of this function, so it's continuous everywhere. For this, check the continuity at let's see 0. So here at 0 there is no break, so it would be continuous obviously. Now if you recall, when you have modulus function, if you have ceiling function, if you have box function or inequality in the definition, then we use right and left limit to check the limits, and finally the continuity. So here I need to find first f of c is 0 here, so f of 0. So what is f of 0? That's a modulus of 0. What's the modulus of 0? 0, 1. Now I'll go for the limit x tends to right and left limit, 0 from right of fx. Okay, now here you again recall the meaning of this. X tends to 0 from right side. Here you have 0, here you have 0 from the right side, that is this side. So here x is greater than 0, so therefore modulus x become x. So what about this limit? Limit x tends to 0 from right, this is x, and as x tends to 0 this becomes 0. Limit x tends to 0 from left of fx. Now what's the meaning of x tends to 0 from left? X is less than 0, that is this portion. So here x is less than 0. If x is less than 0, what's the modulus of x? You know that it is minus x. So this is equals to limit x tends to 0 from left of minus x. Modulus x become minus x. Fx is modulus x. Now this is again in turn 0. So this is 2 and this is 3. So from 1, 2 and 3 we notice that all three are equal. So therefore function f, which is modulus x, is continuous at 0. I'm just giving example at 0. You can choose any point. It's continuous everywhere. Remember, this is continuous everywhere. Function is continuous. Function f is continuous. Function f is continuous at 0. So this way we can check the limits. Mainly limits is based on continuity is based on the limits only. You must be clear with the concept of the limits only. Now here is the next, you can call the result about continuity. The result says that if f and g be two continuous functions, then the first one, their addition f plus g, their subtraction f minus g, their multiplication f into g, their division, that is f by g, and their composition. Now you know FOG and GOF, their composition, FOG and GOF. These are always continuous functions, are continuous functions, are continuous functions. This says that, in another language, this says that summation, subtraction, multiplication, division, composition of two continuous functions is always a continuous function. This is very commonly used result. You will realize if two functions are continuous and if you add them, it would be always a continuous function. The subtraction would be continuous, multiplication would be continuous, division would be continuous, and composition are always continuous functions. And second, these all standard functions, polynomial function, then if you remember all trig functions, polynomial function means it includes linear, quadratic, cubic, anything. Polynomial functions, trig functions, and inverse trig functions, sine inverse, cos inverse, exponential function, which we did at the end of 11th standard, exponential and logarithmic, log. These all functions are always continuous in any proper domain, are continuous in domain, their proper domain, are continuous. These are all continuous functions. You look at the graph of any function, linear function, quadratic function, cubic function. Linear function means straight line. It's always continuous. Trigonometric function. You go back to graph of any trig, sine, cos, tan, you never find break in these functions whenever they are defined, remember. For example, for tan function, you cannot check the continuity at pi by 2 because at pi by 2 it's not defined. You look at the graph of any inverse trig function, and exponential, and one more, that is a logarithmic function, log function. This standard functions, 5 or 6 categories, are always continuous functions. So now onwards, if you see sine, it is always continuous in a given domain. If you see cos, it is always continuous in a given domain. And the one more important, as I explained, summation, subtraction, multiplication, division, and composition of two continuous functions is always a continuous. Let me now come to a simple example based on these two results here. For example, I'll take one function fx equals to, let's see, fx equals to, I'll take sine of x square. Now question is this continuous function? Is this continuous function? That's a question. Continuous function. So answer to this question is yes. Why? Because here one function is sine x, the other function is x square, and you compose them. This is a continuous function. Every trigonometric function is always continuous. This is a polynomial which is a quadratic here. This is also continuous. If you compose them, so sine of x square, this is a composition of these two, So composition of two continuous functions, and therefore it is a continuous. Not only that, even if I would have written like this, sine of x square, this is also a composition of sine x and x square. So this is also a continuous function. Okay. Now if I take this, for example, let me take another example. Fx equals to, I'll take modulus of 10x. In a proper domain, remember, you cannot take here pi by 2. Is this continuous? The question is it continuous function? That's the question. Is it continuous function? That is the question. So answer to this is again yes, it is continuous. Yes, it is. Yes, it is continuous. Why? Why it is a continuous function? Reason is it's a composition of two functions. As which two function? I'll take gx equals to 1, I'll take modulus x. and I'll take hx equals to 10x. Now you find their composition. You know modulus is always continuous function. You know 10x being trig always continuous function. And you do their composition. So which composition then? Their composition, if you do their composition here, that is I'll find g of h of x. So g of hx means 10x, and g means modulus, so modulus of 10x. Then their composition, this is a continuous function. In a proper domain, is a continuous function. So some simple questions you can answer in this way. Composition of two continuous functions is always a continuous function, remember.